So if you are still not sure about the greenhouse effect, like how it really actually works, how we know that these gases are greenhouse gases, and how we know with real hard data that the greenhouse effect is actually getting stronger, we're going to answer all of that today. This video includes easy to copy original sources right in the description. So once you understand the basics, you'll be able to easily understand why arguments like these fall flat. So first things first, we are going to prove that the greenhouse effect exists using just a few physical laws and a pocket calculator. And we start with blackbody radiation. So the greenhouse effect works with what is called longwave infrared radiation, which is the blackbody spectrum emitted by Earth's surface at its average temperature, which is around 288 Kelvin or around 59 degrees Fahrenheit. This is Earth's average surface temperature. Any object that has a temperature above absolute zero will radiate infrared radiation according to this blackbody curve. The x-axis is the wavelength of light, and the y-axis is spectral irradiance. You can think of that as how bright it is at those wavelengths. The brightness is usually expressed in units of watts per meter squared. This is a unit we're going to see a lot. Just means watts, like watts from a light bulb, within a 1 meter by 1 meter square. You can also think of brightness as the density of photons, and it's a continuous spectrum. So if we consider, for example, between 9 and 11 micrometer wavelengths, these are the most popular wavelengths. Or for any particular photon leaving Earth, it is more likely to be near that peak than farther away from it. And if you added up all these wavelengths, sum up all of these different photons, you would get the total irradiance. The total irradiance across all wavelengths. Again, we're just summing, so it's watts per meter squared. And if you were to do that for the Earth's surface at 288 Kelvin, you would get a watts per meter squared total irradiance across all wavelengths of about 390 watts per meter squared. And this comes directly from the Stefan-Boltzmann law that we're going to look at in a second. If it helps you, you absolutely could imagine 4 100-watt light bulbs sticking out of the ground. That is how much energy the Earth is on average emitting all the time. Hotter areas are going to be emitting more, colder areas are going to be emitting less. This is a global average value. So in general, as the temperature goes up, according to the Stefan-Boltzmann law, the total irradiance or the total brightness goes up. That peak gets taller. And also, as you increase temperature, the location of that peak shifts to the left. This is Wien's law. As you get hotter, the peak radiation gets shorter and shorter wavelength. At some point, you get into the visible range, which we've all seen. Now, of course, emitting this radiation 24/7 would result in the Earth cooling to near absolute zero pretty quickly if we did not also constantly receive energy from the sun. The sun is the ultimate source of our energy, and it does so thanks to a constant 1,360 watts per meter squared, there's that unit again, that it receives. And again, you can think of that as 13 and a half-ish 100-watt light bulbs in a 1 meter by 1 meter square. You just have to imagine all of the energy kind of coming directly at you. A normal light bulb, it would be spread out in every direction, but we're getting it all from the same kind of point source from the sun. And again, 1,360 watts is just for a single square meter. So if we wanted to know the total watts that the Earth receives from the sun, we would need to multiply it by the entire area of the Earth. So radius of the Earth squared times pi r squared. If it's not obvious to you why we're using a circle area instead of a sphere, the way I like to imagine it, imagine a big whiteboard right behind the Earth. That whiteboard is receiving 1,361 watts per meter squared, exactly like the Earth is, except in that shadow that the Earth is casting. In that shadow, the whiteboard receives nothing. So that shadow is pi r squared of the Earth, and that must be the amount that the Earth is intercepting if it has gone to zero inside of that whiteboard. So it is the area of a flat circle, not the area of a sphere or half sphere. So that gives us total intercepted from the sun by the Earth. We also have the amount that the Earth is emitting per meter squared due to the Stefan-Boltzmann law. That was the 390 watts per meter squared. So if we wanted to take the Stefan-Boltzmann watts per meter square value and get the total watts, again, we could just multiply it by the entire area of the Earth. In this case, we do need the spherical area because the Earth is emitting from all parts of its surface all the time. It's not just during the daytime like we get with the sun. And so we use the area of a sphere, which is 4 pi r squared. So 4 pi r squared times 390 watts per meter squared, That's the number of watts of this big Earth-sized light bulb that we live on. So we have incoming total watts from the sun and outgoing watts from the surface. You can probably guess where I'm going from here. Basically, because the sun and Earth have both been around for a really long time, we can assume that these two are in equilibrium and set them to be equal to each other. The incoming total watts from the sun must equal the outgoing total watts from the Earth. This is what keeps the Earth at a relatively constant temperature. The water is getting sucked through the drain at the same rate that the faucet is filling it back up. And when we set these equal, we can see that the pi r squared terms conveniently cancel out. And since we know the solar constant and everything else is either a constant or cancels out, we are left with just one variable to solve for, and all we need to do is rearrange the terms and solve for T. T being the average temperature of the Earth. Not math we can do in our heads, but a calculator can easily handle it. And in fact, the value that we get is 279 Kelvin, which is actually pretty close to the 288 K that we expected based on our thermometers, our known value of 288 Kelvin. But it's actually a coincidence because we have skipped a very important step. We made a big oversimplification, but luckily it's an easy one to fix. And it is this number right here that is not quite right. That solar constant, I mean, it absolutely is 1361, but the Earth does not absorb everything that it intercepts. It absolutely intercepts all of those 1361 watts per meter squared, but not all of them are absorbed because the Earth is not perfectly black, in short. It contains clouds and ice and snow and grassy areas that are sort of lighter in color. And all of these reflect what the Earth is intercepting with its shadow. And so instead of absorbing that energy, it just kind of bounces off back towards the sun. This reflectiveness is called its albedo. Every planet has one. And for the Earth, we know that value to be around 0.3. So 30% of all of the watts that we receive from the sun are getting bounced back and don't factor into the total energy balance of the planet. So great. We just multiply the solar constant by what we actually do absorb, which is 0.7. And then we get the real answer. 255 Kelvin or negative 18 C or negative 1 degree Fahrenheit. Done. Except that sounds kind of cold, doesn't it? I mean, sure, there are some places on Earth that are that cold, but I would bet for most of you watching this right now, those places are pretty far away. Probably thousands of miles you would have to go to get to a place that's negative 18 C right now. Except, not really. Because even if you are at the equator on a tropical beach, you actually have a place that cold within 3 miles of you. 5 kilometers. Right up there. Right? You go 5 kilometers up, you will be at about negative 18 C, 255 Kelvin. And it's that difference, the 255 Kelvin that we calculate, that the Earth must be radiating at in order to maintain a balance, in order to be emitting at the same rate that we receive our energy from the sun, and therefore not violating the conservation of energy. The difference between 5 kilometers up, where it is 255 Kelvin, and the 288 Kelvin that we enjoy here at the surface, that difference is the greenhouse effect. I'm not telling you that it's caused by the greenhouse effect. I'm saying that temperature difference is the greenhouse effect. If we did not have a greenhouse effect, our surface temperature absolutely would be 255 Kelvin. Like if you were to surround the planet with infrared thermometers, you would absolutely see it measuring 255 Kelvin. That's the average temperature of the planet. Or put another way, look at the Earth at the wavelengths absorbed by greenhouse gases in the lower atmosphere. The Earth would not look like it does here in visible wavelengths. At those infrared wavelengths that the greenhouse effect works with, the Earth would look like this. A thick fog, and you would not even see the surface. From the perspective of the entire universe, if you try to measure the temperature of the Earth's surface, this is its surface, the surface of the thick ocean of greenhouse gases that fill our lower atmosphere. And I hope I made it clear, but I want to emphasize anyway, this is not pollution. This is just the natural greenhouse effect, And this is what it would look like if you could see at infrared wavelengths. The greenhouse gases, H2O and CO2 mainly, they are thick enough, up to 5,000 meters, that the air is opaque at the wavelengths that they absorb. It is opaque until the atmosphere thins out enough by around 5,000 meters that it finally becomes transparent enough, simply because the air is just so thin, to be, on average, the point where photons emit successfully all the way to space. This is the weighted average altitude at 255 Kelvin. This is where the atmosphere contains few enough molecules of greenhouse gas, because the density is just so low, that an average infrared photon can finally escape to space, even if the concentration of those greenhouse gases remains the same. And at that altitude where those photons escape, by definition really, the Earth is at 255 Kelvin. Energy in equals energy out. Now we don't see the Earth foggy like this because we of course see in what we call the visible wavelengths, which these gases are transparent to. And really that's one of the reasons why we evolved to see in these wavelengths. The first reason is that the sun makes a lot of light at these visible wavelengths. But just as important is that the atmosphere that we walk around in is transparent at those wavelengths, because seeing wouldn't do much good if you can't see through the atmosphere that you're walking through. In a pretty real sense, this is why greenhouse gases are invisible. We evolved to see at wavelengths that are conveniently transparent in our atmosphere of our planet. If we saw at the long-wave infrared wavelengths that greenhouse gases absorb, we wouldn't be able to see the hand in front of our faces. Now, we have known about greenhouse gases since the 1800s. The first experiment was Eunice Foote in 1856, and then John Tyndall 3 years later. Some people say Tyndall stole Foote's idea or refused to give her credit because she's a woman. I've never found any evidence for that. Foote's work was not widely published. She was in the US, Tyndall was in Ireland. It's very unlikely that he was even aware of what she was doing. And Tyndall's experiments were also far more rigorous. He clearly understood much better what was happening than Eunice Foote did. And Tyndall was a pretty cool guy. He was one of the early proponents of evolution back when that kind of took some bravery. So yeah, let's not accuse the guy of doing bad things if we don't have evidence. Now, neither of them really understood at a molecular level what was really happening, right? They didn't understand how CO2 was able to absorb heat as they thought of it. And they didn't really understand this mechanism of capturing infrared radiation. But it's important to discuss it here because it really explains why the rest of the atmosphere, most of the atmosphere, is not part of the greenhouse effect. It's just passive, background. So infrared light is, of course, a form of electromagnetic radiation. And if we take the example of water, you may remember from chemistry, is a polar molecule. This is why it's great for dissolving things. It has a negatively charged end near the oxygen and positively charged near the hydrogens. This is because oxygen as an element is very electronegative. It has a tendency to attract electrons much more strongly than hydrogen or pretty much any other element. Meaning that an oxygen atom in whatever molecule it's in pulls on electrons more strongly than those other elements. So because it's pulling on the electrons more strongly, they gravitate towards it, which gives that part of the molecule a little bit of a negative charge. This is true in its liquid state and it's true in its gaseous state. And because of that permanent polarity, a water molecule can spin and rotate all around, meaning you have electric charge that is moving. That movement of electric charge is what enables it to absorb radiation, in this case, infrared radiation. And for water, it's over a large band of wavelengths. Some molecules are going to be a lot more specific, but water, because it's kind of just always polar, has a very large band of wavelength. And this is why water vapor is the most important greenhouse gas. It's not actually because of its concentration. It's because it can absorb at so many different wavelengths. Now, CO2 is different. CO2 is symmetrical. The oxygens sit on either side of a single carbon atom. Those oxygens in normal conditions pull equally strong at the electrons of the carbon atom in the middle and basically cancel each other out. It's like tug of war. So you get no imbalance in the electric charge or magnetic moment there is no permanent dipole. It's neutral at every part. So rotating it around wouldn't work. But you can get electrical variations by bending the molecule or stretching it asymmetrically, like having one of those oxygens stretch while the other does not. Water also does this, by the way. It has its own bending and stretching actions, but for CO2, it is the only way. And there are two that are important. So asymmetric stretching that I mentioned, where one oxygen stretches and the other doesn't, that's called V3, and it's at 4.26 micrometers. So 4.26 micrometers, that's the wavelength of light that it absorbs in order to enter this asymmetric V3 excited state. You also have 15 micrometers, which is for its V2 excited state. This is its bending action. And you can see the 15 micrometers is a pretty popular wavelength in terms of the black body radiation from Earth because it's pretty high on the curve. Less popular from Earth, but CO2 is especially potent at that wavelength, is the 4.26 micrometer. And I say it's especially potent mainly because water vapor does not interact here hardly at all. So it's kind of CO2's special band. So if you hear somebody saying water vapor dominates the greenhouse effect, yeah, it does at its wavelengths, but this is really where CO2 makes its biggest contribution. Water vapor has nothing to do with a 4.26 micrometer band. But a really critical point, these are not exact numbers. You can think that these photons, like if a photon of 15 micrometers hits a CO2, it's not guaranteed that it's going to bring it into one of these excited states. It's just that is the wavelength where it's most likely to succeed. But as you get farther away from those wavelengths, it can still succeed. It can still enter the same V3 or V2 excited state. It's just less likely the farther you get away from those sort of optimal wavelengths. And that's a key point that we're going to come back to in a second. So if an IR photon is at just the right wavelength, or at least close enough, it can be absorbed by a CO2 molecule, which then causes that molecule to enter one of these two excited states. Which state depends on whether it was a 4.26 adjacent photon or a 15 micrometer adjacent photon. And once it is in an excited state, within a few milliseconds, it will re-emit that photon back out of the same wavelength. And when it re-emits it back out, it will reduce back to its sort of relaxed state. Or at least this is what will happen if the CO2 molecule is by itself in the middle of space, for example. It will re-emit it back out within a few milliseconds. But down here, on the densest levels of the atmosphere, right above the surface, CO2 is not by itself. It is bouncing against many other molecules, usually a oxygen or nitrogen molecule, and that happens a lot, billions of times per second. A CO2 molecule is getting bumped around by a nitrogen or oxygen molecule. And if that CO2 molecule is in an excited state and a nitrogen or oxygen molecule hits it just right, it can take the energy from the excited state and turn it into translational motion of that nitrogen or oxygen molecule, also known as speed of molecules, also known as temperature. When a photon is absorbed by a CO2 molecule, before it can be re-emitted out again, it is almost always converted directly into the speed of another air molecule, usually N2 or O2. And in this way, the absorbed photon that would have otherwise passed right through those oxygen and nitrogen molecules and gone right to space, the energy of that photon has been converted into heat in the lower atmosphere by directly warming an air molecule. So instead of the energy of the photon leaving, it has been stopped and converted into heat in the atmosphere. And this is why you don't get a greenhouse effect with nitrogen or oxygen. You cannot bend or stretch an O2 or N2 molecule in any way that will result in an imbalance of charge. And if N2 and O2 can't make it work, lonely argon, of course, never had a chance either. Now, this is just explaining how it works for those interested and to explain why the rest of the gases in the atmosphere are not greenhouse gases. I'm not giving you this theoretical explanation in order to prove to anyone that CO2 is a greenhouse gas, because proving it is actually way easier. Yes, we have these historical experiments, they're kind of neat, but of course we are in the 21st century now, we can measure these things way better. Devices that measure CO2 for purposes totally unrelated to climate change, by the way, utilize this fact that CO2 is absorbed by 4.26 micrometer infrared light or 15 micrometer. Usually they use 4.26. So you can see here, for example, this really neat animation from the Vaisala company. They make CO2 devices for industrial greenhouses. In hospitals, humans, of course, emit CO2, and measuring the amount of it can be useful in diagnosing conditions. So there are devices measuring CO2 concentrations in our breath. There are transcutaneous ones that measure CO2 in our blood. There are CO2 sensors for air conditioning units. HVAC systems that recirculate air to save energy must measure CO2 to make sure it doesn't reach unsafe levels. In laboratories or manufacturing facilities, there are general-purpose infrared spectrometers, very widely used devices. Food safety analysts measure CO2 concentrations of food packages to check for contamination. There are home indoor air quality monitors that measure CO2, like Aranet 4. Beer brewers have specialized devices. There are portable devices to check CO2 levels on public transportation, for example. And there are educational units. Devices that cost $200 can measure CO2 to within 2 parts per million. And all of these devices work because CO2 absorbs infrared radiation at known wavelengths, which is exactly the reason that it is a greenhouse gas. These wavelengths are emitted by the Earth. If CO2 were not a greenhouse gas, none of these devices would work. And I emphasize this because I have absolutely seen people try to question the experiments of Foote and Tyndall as if everything in climate science would fall apart without them. Like, you probably entered a building today that has one of these CO2 measuring devices. Now, we explained already why nitrogen and oxygen are not greenhouse gases. There's no way you can stretch them or spin them or anything else to get an unbalanced charge. It's just two atoms of the exact same electronegativity stuck together. And this, I think, is the main answer to those who say CO2 is only 0.04%. Like, wow, what a small number. I mean, if 99% of the atmosphere doesn't interact with infrared at all, it may not even be there. Why are you dividing by it? You may as well divide by the entire mass of the Earth. And I've seen at least more than once somebody try to counter this "it's only 0.04% line with arsenic, saying that arsenic can kill you in very small doses. Okay, not a very good analogy in my opinion. Like, what does the poison of a biological system have to do with the question of whether or not light can be absorbed through a medium by something with a low concentration? Because this is exactly what we're talking about, right? The question is whether or not that 0.04% of the atmosphere is thick enough that it can absorb light passing through it. So I have here in the picture behind me 2 liters of crystal clear tap water. You can see it right here. See that you can see me just fine. You can see my hand passes straight through it. The light from my light up there passes right through it, and you can see it fine. This is 2 liters or 2,000 milliliters. And I have here some brown paint left over from when I painted that wall. Yes, I chose that color. Leave me alone. And a little syringe. If we did 0.04% of 2,000 milliliters, that would be exactly 0.8 milliliters. This would give us a perfect 0.04% or 400 parts per million. So let's just see. You can see it here. So this is a 1 milliliter at the top. This is 0.8 that I filled it up to. And we take it and we put it right into here. Why did it clump up like that? I'm going to use this clean knife just to stir it up. And there we go. So this 0.04% of paint made it so that the light can no longer pass through. It is opaque to the light. And I love this example because it's not even really an analogy. This is what we're talking about. The only difference between this and the 0.04% making a difference in the greenhouse effect is that we're using visible light instead of infrared, and we're using water instead of air. but it's the exact same concept. 0.04% is plenty to make the medium opaque. And by the way, this picture is just a few inches thick. The 0.04% of CO2 in the atmosphere goes up thousands of feet, thousands of meters, right? This is just a few inches wide. All right. I'm just going to leave this here for the rest of the video. There's more than enough CO2 molecules at the surface to interrupt the infrared radiation. There's actually like 10 to the 22 molecules per cubic meter in that 0.04%. Plenty. All right. And actually, you do sometimes get the opposite argument that there's just so darn much CO2 in the atmosphere that adding more cannot possibly make a difference. This is often called the CO2 is saturated. And so they question, they say the atmosphere is already opaque to CO2. How can adding more of it possibly cause warming? It's an excellent question, but it's still pretty easy to work out the answer. So if we look back at that cross-sectional view of the atmosphere, it is absolutely true that adding more CO2 in these dense surface layers will not make a difference. The atmosphere is fully opaque here to the CO2 wavelengths, but what about the top of the greenhouse gas fog, where the Earth emits at 255 Kelvin? After all, the atmosphere is very well mixed with CO2. If we have 420 parts per million down here at the surface, we also have 420 parts per million 20 kilometers up. CO2 mixes very quickly and very evenly across all layers of the atmosphere. What changes as you go up is the total air density, but the relative concentration of CO2 stays the same. That reduction in density is why we get the emission at 5,000 meters. This is where the air becomes thin enough that those greenhouse gases still don't make a difference. But it's not because the CO2 concentration is less. It's like competing variables. How much CO2 concentration do you have? Combined with how dense the air is, those two together determine whether or not the atmosphere is opaque or transparent on average at that level, at that altitude layer. So now imagine we zoom in right at that 5,000 meter layer. Now we're just a few meters above it. And now imagine we increase the CO2 concentration everywhere from bottom right up through this 5,000 meter layer. Let's say we increase it from 300 to 400. It increases at the surface, it increases at 20 kilometers, and it increases right above that line where it was before free to escape. But since we have added to the number of CO2 molecules, the density hasn't changed. The air density is the same, but the CO2 concentration has increased. It means that 5,000 meter layer where it had become just thin enough for the photons to leave, now it's not thin enough. Now you have to go a little bit higher to get to a slightly even less dense part of the atmosphere than you did before. And by going higher, we are at a colder altitude. And this is not a big effect. It's on the order of a few dozen meters. But it's just enough to make the air colder. And so now the Earth is not radiating at the 255 Kelvin that it must be in order to balance out the incoming solar. It's emitting from a lower temperature, which means by conservation of energy, it must be accumulating energy. And it will continue to accumulate energy until it settles into a new equilibrium. We're not there yet. And in fact, every year that we increase CO2 concentrations further, we get farther and farther away from reaching that new equilibrium point. Less infrared radiation is escaping to space, more of it is being accumulated near the surface. The second reason that the CO2 is saturated argument does not work, it's that even though CO2 absorbs at 15 micrometers, for example, as we mentioned, it's not 100% at 15 micrometers and 0 at 15.01 micrometers. It just gets less effective as you get farther away from that optimal absorption wavelength. The fact that it can absorb at those other wavelengths actually has a lot to do with those nitrogen and oxygen molecules bumping into it. It sort of shakes it up and kind of throws it off its normal groove, but the meaning is it can vibrate at different frequencies because of that broadening of its absorption lines by those other molecules banging into it billions of times per second. So it can always absorb at a greater wavelength band than just 15 micrometers, for example. Increasing CO2 concentrations then, it doesn't mean that it can absorb from other wavelengths. It can already absorb at those other wavelengths, just not quite as well. Remember, a photon of 15 micrometers hitting a CO2 doesn't always result in this absorption and transition to an excited state. It's just most likely at 15 micrometers, and it's less likely as you get farther than that. But as you increase CO2's concentration, you simply have more chances at those outer bands, those falling off points from 15 micrometers. You have a better shot just because there are more molecules now in the atmosphere. 50% more, right? So 50% better odds than you had before at any particular wavelength you want to arbitrarily choose. This is where the warming effect comes. This is what's called the wings of the absorption spectrum. You can see, for example, here, this is a peak showing 15 micrometers. All of those little red dots around the peak are statistically significant increases in absorption. This comes, by the way, from a paper Liu et al. 2022. This is real data. This is not a theoretical chart. This is a ground station measurement showing that the radiative forcing away from the peak is increasing. The peak is not statistically significantly increasing, but the wings around it are. This is a measured effect. So we're going to look at this paper and several others. Papers like this one that use ground-based instruments to detect the extra radiation coming down, as well as papers that use satellite instruments that have measured the reduction in radiation going back out to space. So the first ever paper published that looked at energy emitted by the Earth from a satellite was Hanel and Conrath 1970 using the Nimbus 4 satellite. The Nimbus series of satellites were actually the second generation of Earth-observing satellites that were launched. And then later in 1989, we had Raval and Ramanathan 1989. This was the first to actually quantify specifically the greenhouse effect and its dependency on sea surface temperature. These were both pretty early studies and didn't yet look at changes in the greenhouse effect. The first paper to do that was Harries et al. 2001. Very famous paper. It used actually the same satellite that Hanel 1970 used, the Nimbus 4. They took Nimbus 4 data since 1970 and combined it with results from another satellite, the Advanced Earth Observing Satellite, that was launched in 1996. And between that 27-year period, they were the first one to see that the brightness temperature, which is measured as outgoing infrared, showed a measurable decrease at wavelengths associated with long-lived greenhouse gases, especially CO2 and methane. So they show that the radiation is leaving from a higher altitude, meaning the Earth is emitting less than it needs to in order to balance incoming solar. So it's a direct measurement. Harries et al. 2001 was a very important paper, but it was just the first paper. 2001 was 24 years ago. And I'm sorry if that's hard to hear. It was also hard to say. But it was 24 years ago. And in that time, we have continued to refine and measure these effects. And we're going to take a brief look at all of those papers. So next, we have Filippona et al. 2004. They used ground-based measurements. These are called purgeometers. A purgeometer is a device that measures infrared radiation. So they use these to measure downwelling infrared radiation trends from 1980 to 2002. So Harries et al. Looked at it from space. Filippona et al. Looked at it from the surface. And they saw a statistically significant increase in downwelling infrared. Again, complementing the decrease to space observed by Harries et al. 2001. So we have it from both sides now, an increase at the surface and a decrease observed from space. And again, these are just the first studies of their kind. So let's see how much it has advanced since 2004. In 2007, we have Griggs and Harries. This was similar to Harries 2001, but remember that looked at data from 1970 to 1996. This study extended that by taking data from a third satellite, the Aqua, that was launched in 2002. It's actually still operational. And this study both confirmed the trend was increasing and continuing through to 2003, but it also gave it an additional weight because it's a third satellite. It's a new data source that also agrees with the other two. In 2009, we have another ground-based study, Wang and Liang 2009, similar to Filippono 2004, but Filippono 2004 took its data only from within the country of Switzerland. Wang and Liang extended that to stations in the US, Europe, Africa, Australia, and Asia. Again, ground-based measurements. You can see one of the stations. This is a station from part of the US network here. This is a per geometer at the site in Illinois. And the study concluded downward long wave radiation increased at a rate of 2.2 watts per meter squared per decade from 1973 to 2008. Next, we have Chapman et al. 2013. This is another satellite study. It was also using the Aqua satellite, which we saw from Griggs and Harries 2007. This one was interesting because it looked at the period 2002 to 2012, which is special because the planet didn't really warm during that time. It was kind of a pause in the warming. So this allowed for an opportunity in a way to get a clean signal of the radiative forcing without a background of increasing temperatures, which also affects the infrared escaping to space. A year after that, another study, Gastineau et al. 2014. This used a string of NOAA satellites, NOAA 6 through NOAA 14, which all had on board the same instrument called HIRS or HERS. And this study is the longest continuous satellite record of 25 years. And they found while the tropical ocean surface temperature has risen by 0.2 K from 1982 to 2004, the reconstructed outgoing long-wave radiation remains stable over the ocean. Consequently, there is an increase in the clear sky greenhouse effect of 0.8 watts per meter squared per decade. Next, we have Feldman et al. 2015, another surface-based study, but using a different type of instrument. The studies that we saw so far use per geometers. This one uses a technique called Fourier transform infrared spectroscopy, much more advanced and precise than a per geometer. They measured the precise increase in radiative forcing of the increase of CO2 from 2000 to 2010, which was 22 parts per million. So it increased by 22 parts per million atmospheric concentration between 2000 and 2010. And they found that the CO2 radiative forcing increased by 0.2 watts per meter squared. Just in that period, just from that increase of 22 parts per million between 2000 and 2010. So this was a way to better quantify the per parts per million radiative forcing. We have another surface-based study, Wild 2017, using per geometers from a network called the Baseline Surface Radiation Network. And you can see the trend, a very clear increase. The author notes, I obtained an overall mean increase in downward thermal radiation of 2 watts per meter squared per decade since the early 1990s. This change in downward thermal radiation quantitatively agrees very well with the respective change calculated by the latest generation of global climate models. And we jump to 2021, starting with Whitburn et al. 2021, and we return back to satellites. And we have a new satellite, the European Space Agency's MET-OP, or Meteorological Operational Satellite, launched in 2006. Again, like the rest of these satellite-based studies, we see a decrease in outgoing infrared. In particular, the increase of atmospheric CO2 in CH4 led to significant negative trends in the clear sky, spectrally resolved outgoing long-wave radiation of negative 0.05 to negative 0.3% per year in the spectral region corresponding to the V2 and V3 CO2 and in the V4 CH4 band. V2 and V3, remember, are the main excited states of the CO2 molecule, the bending and the asymmetric stretching. Next, we have Kramer et al. 2021. This study took everything a step further and measured for the first time, directly measured greenhouse gas radiative forcing using a method called radiative kernels, for which they cite this paper for inventing this method. Now, the satellites they use are not new. We use the same Aqua satellite we saw with Chapman 2013 and a few others, as well as the Terra satellite, but it combined it with real-world data from CloudSat, another satellite. So they used this radiative kernel technique to essentially peel away other influences on the changes in outgoing long wave. and isolate just the change, just the radiative forcing from CO2 specifically. And they found it increased. They're using satellites, but they're speaking from the perspective of the surface here. They show that it increases by 0.53 watts per meter squared from 2003 to 2018. You can see the chart here. In their words, this serves as direct evidence that anthropogenic activity has affected Earth's energy budget in the recent past. Then we come to Leo 2022, which we already saw. Another surface-based measurement using the AIRS network. The CO2 absorption band centered around 667. That's the wave number, by the way, which you flip it around and you get back to the 4.26 micrometers wavelength. The trends are generally positive. Radiance is increasing over time and are statistically significant in the band wings. So again, this is direct observational evidence that CO2 is having a radiative forcing due to those wings where it doesn't absorb as effectively as it does at the peak. Next, Raguraman et al. 2023. This also uses the Aqua satellite covering the period 2003 to 2021. By conducting global line-by-line radiative transfer simulations with 2003 to 2021 meteorological conditions, we show that increases in CO2, CH4, and N2O concentrations cause an instantaneous radiative forcing and stratospheric cooling adjustment that decreased outgoing long-wave radiation. And I mean, I love this graph. I mean, just look at this graph. I mean, you really have to have an especially aggressive level of bias to see a graph like that and still not think that the greenhouse effect is getting stronger. All right, last two, both in 2024. First is Teixeira et al. 2024 using Aqua. In case you don't see the trend here, older satellites are pretty good and useful because you have the same instrument measuring over time. You don't have to try to stitch together different satellites, different measurements at different altitudes and all that. You can just kind of keep the same satellite and easily observe trends over time. You have to make some corrections, but it's a lot simpler than trying to stitch together a lot of different satellites. And they used a new way to isolate the CO2 signal from that of temperature and water vapor. In their words, this is the first time that the spectral signature of the increase in CO2 isolated from temperature and water vapor changes has been directly observed from space. And you can see here, this is the average per year difference that they saw over a period between 2003 and 2012. And finally, the latest comprehensive study, Omura 2024. We return to surface per geometers, also from the BSRN and SURFRAD network. You can see a map of the stations here. Not sure who thought it was a good idea to use black stars on a black and white map, so here's a version with red stars. They calculate radiative forcing based on real-world data at the surface, as opposed to calculating it with respect to the top of the troposphere, as is usually done. So the mean radiative forcing for the surface during the first 2 decades of the 21st century is 0.05 watts per meter squared per part per million of CO2. So every 1 part per million, resulting in an extra observed downwelling from the perspective of the surface of 0.05 watts per meter squared. You can see the trends from 2 stations among their included charts here. So kind of related to a lot of these studies, we know that the greenhouse effect is getting stronger because we can measure that the upper atmosphere is cooling. We can see this at every layer of the atmosphere, not just the stratosphere. You can see I cite here 3 papers for each layer of the atmosphere. Each of these papers measured cooling at that respective layer of the atmosphere, which is absolutely consistent with a greenhouse gas induced warming in the lower troposphere and totally incompatible with an explanation of the warming that comes from the sun. Also inconsistent with a strengthening sun or reduction in cloud cover kind of explanation, 2 effects that would only really work during the day. The greenhouse effect works day and night. And since nights are generally cooler than days, relatively, proportionally, the effect is greater at night than during the day. This means a strengthening greenhouse effect should induce a warming that happens faster during nights than during days. Put another way, the difference between the hottest part of the day and the coldest part of the night should be decreasing because the nights are warming faster. They're kind of catching up to the daytime temperatures. So the difference between the two is less. That difference is called the diurnal temperature range, and it absolutely is decreasing and has been measured in many observational studies. For example, this one here. Also here, 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 and here. I always make a point in my videos to use real world data as much as possible. All of the studies that I cited here were based on observational evidence, real world data. It's sort of become a theme on this channel. And I choose those papers just because I think they're more powerful. I mean, real world data, can't beat it, right? An instrument on a satellite cannot be coerced. It cannot accept bribes. It cannot harbor fantasies of communism or whatever the hell the conspiracy theorists are saying today. It's just measuring data. So I show these and tend to shy away from model studies, but it's not because I distrust models or think that they're wrong. Housefather 2020 showed quite clearly that historically models have been pretty accurate in their predictions. And it's certainly not that I don't think they have a purpose, because regardless of how much trust you want to put into models, regardless of whether or not you think they are being biased, you at the very least cannot claim that there's no reason to use them. Because all I have shown you today is that the greenhouse effect exists and it's getting stronger with a radiative forcing watts per meter squared that we can measure. I cannot similarly show you evidence that a doubling of CO2, for example, will lead to a particular amount of warming by 2100. It can't be calculated with one equation or taking two laws and setting them equal to each other. All we have talked about so far is the flow of radiation, and that is a big part of it. But below that 5,000 meter line, a lot of stuff happens. You have convection, ocean currents, wind patterns, evaporation, including water vapor feedback, clouds, all different kinds of clouds, transpiration, condensation, precipitation. These all depend on their own sets of physical laws and initial parameters, and many of them also depend on each other. Change temperature and all of these other things change. You cannot strip this question of how much warming we will get over a particular time period into a pen and paper exercise. It's just far too complicated, and you certainly can't reproduce the Earth in any kind of meaningful way in a box in a laboratory. That experiment would be useless. The only way to calculate this is with a powerful computer. You actually need a supercomputer to run all of these calculations one time step at a time. And even those computers, supercomputers that fill entire rooms, take weeks to run these simulations. And you can question the accuracy of models or the motives of those running them if you like, hopefully with some actual evidence, but you absolutely cannot claim that there's no reason to use them. Because short of building another planet Earth right next to this one and filling it with CO2, there is no other way we can try to answer this question. And if you feel that the evidence I've laid out is clear, that the greenhouse effect is absolutely increasing, then I do think that you and everybody else living on this planet should have an interest in knowing where we're headed. We are all living in this uncontrolled experiment. And I think anybody who's participating in this experiment by living on this planet should be interested in knowing where we're headed. And I think that'll do it for me.